today we're going to talk about how to detect data drift, or also known as covariate shift, and how we can really use that knowledge to try to figure out what has gone wrong with our models after it has been deployed to production. And we're going to have a theoretical part first, and then I'm going to go over what is data drift and what is covariate shift and how it can impact performance. And then we'll go over the algorithms that you can use with NannyML to detect covariate shift. And then we'll finish with a practical deep dive in a Jupyter notebook that I prepared that you also can access on GitHub, just going through a real data set when we'll see that there's some drift, and we'll try to spot how it happened and where it is. So let's get started with quickly setting the stage, just to give you a kind of a perspective why it's important. So imagine that you're trying to predict so mortgage defaults. You work at a bank, you try to predict mortgage defaults. So in order to develop a model that can predict whether somebody is going to default on a loan or not, you're going to take their credit scores, their customer information, and hopefully you build a model that actually predicts loan defaults reasonably well. And to give you a bit of information about how it works in practice, normally you would want to wait entire duration of the mortgage, let's say 20 years or 30 years, to get your targets, but that is not really practical. And for vast majority of customers, you can already know whether they're going to default or not. And in reality, most banks use some kind of proxy targets for that. As an example, we can say that if a person is delayed 6 months or more in the repayment of the mortgage after 2 years of the loan beginning, then we can say that this person is practically defaulting. So that can be the target. And here, of course, it means that we still need to wait 2 years after we've deployed our models and made the prediction to really see whether this prediction was correct or not, which means we cannot easily evaluate the quality of the predictions. That means that we need to somehow try to estimate that performance. And I already gave a webinar last week about that. So if you want to learn more, then ping me on LinkedIn after the webinar, and I'll gladly share the link with the recording. And now we're going to assume that we actually have access to targets, and somehow something has gone wrong, and we need to figure out what went wrong. And what are the steps? So the first step is going over the ML monitoring flow, so something that already kind of covered, which is what should we do first, what should we do second, what should we do third, how do we go from starting monitoring to resolving any issues and making sure that we can actually protect the business impact of our models. Then we're going to define covariate shift, which is one of the 2 main reasons why machine learning models can fail and the easiest one to spot. And then vast majority of the webinar is going to be about actually delving deeper into the algorithms we have at our disposal to try to figure out where is data drift, how strong it is, and whether it's potentially linked with the drop in performance. And for that, we have Univariable drift detection when we look at one feature at a time, and we have the Multivariable drift detection when we'll try to look at a group of features or even entire data set at once to really try to figure out whether there is some significant drift in our data. So let's get started with the first part, the monitoring flow. And I'll just quickly go over that. So we have the 3 goals of monitoring. First, we want to maintain the business impact of the model. This is kind of an obvious thing where you develop your machine learning models, they serve a purpose and hopefully drive business impact. And if the models deteriorate in production, and vast majority of them do deteriorate in production or they degrade in production, we need to do things, we need to know what's going on, and then we need to take actions to maintain the business impact of that model. Second thing is reducing the risk of the model, because the predictions are uncertain, and there is a certain risk that every machine learning model basically imparts on the organization. And as long as the model is predicting reasonably well or predicting in line with expectations, this risk is known. However, if the model degrades, this risk can really balloon out of proportion. So what we want to do with monitoring is to really know and quantify the risk of the model. And the last thing, for you as a data scientist or for you as a head of data science, you want to increase the visibility of the model to either to basically gain recognition and make sure that your work is well rewarded by either hopefully getting promotions or getting raises or getting higher budget allocations for a team. Now for the process, we start with performance monitoring, and again, that's something that I covered in the previous webinar, when we want to make sure that we know the performance of our models at all times, whether ground truth is available or not. Then we go into the root cause analysis. So assuming something has gone wrong, and only if something has gone wrong, then we need to figure out what has gone wrong. So then we can go into the issue resolution and try to resolve the problem. And today we're focusing mostly on the second part, which is the root cause analysis. And to actually do root cause analysis, we'll have to look at data drift and what exactly changed in our data. And hopefully you can also find out the actual causes of the drop in performance. So that is really the flow. And now we can start with the second part, which is the covariate shift. So let's start with the defining of what covariate shift is. And we can quickly define covariate shift as the change in the joint model input distribution. So imagine that you have multiple features comprising of your model inputs. And if this joint distribution changes in any significant way, then we can talk about covariate shift. To give you a simple example here, imagine that we have just one feature. And if the distribution that we sample from population, so we have some kind of sampling function. If that sampling function from population to our sample changes, we have covariate shift. And that means that not only the model input distribution will change, but potentially also the target distribution is going to change, because we might move from a region when, let's say, there is more positive class instances to a region when there is more negative class instances. Like in the example here, we see that we have in total more negative class instances compared to the before the shift. And that also might potentially impact the performance of the model if we move from regions when the model is supposed to perform well, because maybe it's very easy to separate classes, to region when the model is not going to perform so well, maybe because it is hard to separate the classes, or maybe because it did not have enough data to really learn the correct pattern. And of course, the same applies to regression problems, but it's a bit easier to talk about binary problems and binary classification problems, and to visualize binary classification problems. So let's stick with that. Now, of course, as I mentioned, we're talking about a joint probability distribution. So just to give you an example why this joint part is important, there are kind of covariate shifts when, if you look at every single feature separately, you will not really see a difference. So imagine that here, due to some kind of error on the data preparation or data engineering side, or maybe somewhere in your data pipelines upstream, feature 1 and feature 2 gets switched sometime between week 10 and week 6. And you look at those distributions, and if you look at the distribution separately, it's gonna look basically exactly the same. If you look here, the distribution is Gaussian, and the distribution in week 10 and week 16 are basically the same, but almost to a rounding error, and the same follows here. But of course, our distribution is completely different, and the model is going to make terrible mistakes because it assumes that feature 1 is feature 2 and vice versa. So this is something that we absolutely need to be able to detect, and it's something that can actually let us identify what is the potential root cause of the performance drop. So now we know what are potential problems with machine learning models in production, that they deteriorate, and one of the main causes is covariate shift, and how it looks like, what it is. Now let's talk about how to detect it. So let's assume that we have a model, there is a problem, we need to figure out what exactly went wrong. So the first avenue that we can go with is Univariable Drift Detection. And what does it do? So first of all, it's going to capture the change in distribution of a single feature. And because it's going to look at the distribution of a single feature, with NannyML, it's going to automatically kind of loop over all features in parallelized way, and you will see all features separately and how the distributions of those features is changing. But there's, of course, a few things that it cannot do, and the most important one is that it cannot detect changes in correlations between features, or any really change in relationship between features, whether they're correlations or maybe something a bit less linear. And because imagine that you have a model with 70 features or 100 features, which is pretty standard in models that are deployed to production. If you look at every single feature separately, it's quite likely that some of them will shift, even though it doesn't impact performance or it's not the root cause of the problems that we might have identified with our performance monitoring. And that means that it can suffer from high positive rates. If you have 100 features and you want to do your monitoring daily, you'll almost certainly get a lot of false positives of things that are meaningfully changing, but they are not really the real problem. So you will just drown in alerts. And this is really one of the main reasons why univariate drift detection cannot be used as a kind of quality assurance tool, and you need to do performance monitoring. And instead, you should use univariate drift detections to really drill down on where the problem exactly might be after you've identified issues using performance monitoring. So now we have in our open source library 6 different methods for univariate drift detection. And at some point, I will make another webinar probably going over all of those in depth and discussing the pros and cons, but that is really going to take at least 1 hour. So this time I'm going to focus just on one that we recommend as a default and we have as a default in our library. And this is the Jensen-Shannon distance. And why we recommend those is, first of all, it is a method that's quite good at detecting most of the significant shifts. So if you have a significant shift in your data, in your feature, it's going to be able to detect those most of the time, almost all the time. It is also quite robust against outliers, unlike some other methods. And few huge outliers or few anomalies in the data will not necessarily trigger that. So that already reduces the false positive rate or false alert rate. And of course, no method is perfect. That's why we have 6 of them, not just this one. And one of the main issues with Jensen-Shannon distance is that it is potentially a bit too sensitive to small drifts. So you're still getting that false alerts here and there. But as long as you use it only as or mainly as a root cause analysis tool or kind of figuring what's going on tool, you should be fine. And now I'm going to go over this method a bit more in depth, talking about the inputs, the results, and the kind of intuition of how this method actually works and what it does. So let's start with practical things. So what are the things that we need to have? So the first thing we need to have is we need to get the features that we actually want to analyze, that we want to try to see if there's any drift. So we just provide column names for which we want to do our analysis. And then in our univariate drift calculator, which is kind of a high-level interface for any of the univariate drift detection features, we can specify, and we actually need to specify what methods that we want to use for drift detection. We can use more than one as a list. And the same we need to do for categorical methods, because some methods work only for continuous data, some methods work only for categorical data. One of the many strengths of Jensen-Shannon is that it actually works reasonably well for both categorical and continuous features, so we can use it for both. And now let's move to how this thing actually works. So here I have a kind of a presentation that should build a bit of intuition about what's going on. So we have here probability distribution functions. The reference one is, let's say, your test data, for which you know everything was fine and the distribution looked like it should look. So we have a binary bimodal distribution here, comprised of kind of 2 normal distributions, one centered around 0 and another centered around 5. And this is our reference distribution. Now, let's say that we wait a few weeks, few months, and we detect that there is some issue with performance. So then we're going to want to compare our reference distribution to the, let's say, a week or a day for which we know that there is a problem. And for that, we'll look at our analysis distribution for a given feature. And we see that it has significantly changed. And there is one peak exactly at 0, and there is another peak this time at 10. So maybe again, some problem upstream in our data engineering pipelines when something was maybe not scaled or scaled inversely or just multiplied by 2 for some reason. And we see that there is significant change. And what JS actually provides us is an average distance between the distributions for these two distributions. So we see here that the analysis distribution is completely flat and reference distribution is quite high. So it's going to take this difference and halve it, and then it's going to do the same thing here between analysis and the reference and analysis. So in essence, it's actually quite similar to KLR divergence, but the difference here is actually it doesn't only look from the perspective of difference between reference and analysis, but also from the difference between analysis and reference. So it's kind of like a KL divergence, but from both sides. And that is basically what our JS distance tells us. So now we kind of have a at least cursory intuition of how the method works. Now let's look at the results. So what we get here is our distance metric. So Jensen-Shannon distance goes between 0 and 1. And we see here that it is quite low. So we know that for this specific example, everything is doing fine. We have our threshold. If this threshold is exceeded, we know that there is a significant increase in our drift, and this threshold is generally automatically done by NannyML, automatically defined by NannyML, using the variance of this Jensen-Shannon distance or any other distance in our reference dataset. So let's say our test dataset. And if there are some alerts, then of course we will see also the alerts. And that's really kind of an overview of what you can do with univariate drift detection methods and an example of one and how it works. Now let's go to multivariate drift detection. So here, let's start again at what does it actually do. So the first thing it does is it captures any linear change in relationship between features. So this is kind of the answer to the problems of univariate drift detection features that couldn't actually detect any kind of change in the correlations between features. The idea of multivariate drift detection is it actually can capture that. So it can capture the change in my second example that you saw with distribution 1 and distribution 2 switching places. It also captures changes in single feature distributions. So it kind of does the same thing as univariate drift detection models, but on a more global level. And of course, there's there's some drawbacks to that. And here I want to mention two, which is one, it requires at least 2 features to work because of the way the algorithm works that I'll explain in a minute. We will be doing dimensionality reduction at some point, and to reduce dimensionality, we need to have dimensions to reduce, which is not going to be a problem for almost any data set. Because you always work with multiple features in machine learning, apart from maybe some kind of time series analysis. And there's another issue is that because we're looking at multiple features at once, it's not as easily interpretable. But there's good news is that we can select a subset of features on our data to kind of try to narrow down where the change in data structure has actually happened. So we still get a bit of interpretability there. And at the end, we can come back to univariate drift detection to see whether the change in data structure is due to change in single feature distribution or correlations between features. So again, let's go over the input. So the first thing here is, and the only thing, fortunately, is we need to provide feature columns for our data reconstruction calculators, and we'll just provide the data for our features. We could also put in our model predictions, but that would mean that we're not really looking at only the covariate shift, but the entire distribution of model inputs and predictions at the same time, which is kind of a different thing. So we recommend that you take that you put only your features for multivariate drift detection. And the results, again, quite similar to before, when we have our reconstruction error, which is a measure of drift, and I will go into how we can obtain it and walk you through step by step of the algorithm that we use. Then again, you see confidence bands, which is basically how confident that our drift metric is within certain range. These are the ranges. And we have the threshold. And if the thresholds are again automatically determined based on the behavior of the metric on the reference dataset. And if if there is drift in your data, you will see that these thresholds will be exceeded in time. And then we have alerts, the small red diamonds that show you that something has gone wrong. Now let's start building the intuition of what's going on in this algorithm. It looks a bit complex, but actually the premise is quite easy. So the main idea is that we're going to train or learn a compression decompression part. So let's say that we're going to train something like an autoencoder. And this autoencoder is going to learn the actual structure of the data in order to minimize the reconstruction loss, so the loss between the original data and the reconstructed data. And the key thing here is that we're going to rely on this compressor to correctly learn the structure of the data, and then we are going to measure the loss of this, let's say, autoencoder, to measure how strongly the structure of the data has changed. So this is really the high-level intuition. So imagine here we have the compressing part of the autoencoder. We compress it to latent data, latent space, and we decompress it. And then what we're going to do is we're going to compare the original data with reconstructed data, like I do here. And for every place where they don't really align, we're going to be able to compute the reconstruction error. So now that you have the general idea that we're going to rely on this autoencoder to learn the structure of the data, and then we'll measure how good this autoencoder is on new data to see whether there is significant change in the data structure. Let's go into the actual step-by-step algorithm. So how do we train it? So first we'll have to prepare the data. I'm going to walk you through with how we train the algorithm in NannyML. And we actually don't use autoencoders. We use the simplest possible thing, which is the PCA, because we don't need to capture the structure of the data fully. We just need to capture it well enough that if there's change in the data, the loss of the encoder-decoder changes. So it doesn't need to be low to start with. So we're going to prepare the data to make sure it can work with PCA. We're going to impute missing values. We're going to encode categorical features. And at the end, we're going to scale the data. Then we are going to train fit a PCA on our reference data. So it could be the test set, could be any part of your data, any period in the data for which you know everything is fine and there is no significant data drift and performance is satisfactory. So that what we're going to do is we're going to compress and decompress. So we're going to do transform and inverse transform of this reference data using our trained PCA, and this trained PCA again was trained on reference data. Then we're going to compute the distance between the original and the reconstructed points. So the points that gone through the compression, decompression using PCA. And we're just going to do the simplest thing. We're going to compute Euclidean distance between every pair of points. And then we're going to compute so-called reconstruction error, which means that we just take all the distances, all the Euclidean distances between those points, and we take the average of that. And for that, we know what is the general loss or the general reconstruction error of our PCA on reference data. It's not going to be 0 because it's lossy. We still need to reduce dimensionality. We're losing dimensions, which means we are losing information most likely. So we have some kind of reference reconstruction error. Then when we go into the drift detection mode, what we're going to do is we're going to look at our analysis data, so the data for which we want to figure out whether there is drift, and we're going to compress and decompress this analysis data using the trained PCA. And the important thing here is that we do not retrain the PCA. We use the PCA that we fitted on our reference data, and this PCA still remembers, and of course in quotes, what is the structure of our reference data. And then we're going to do the same thing. We're going to compute the distances between original and reconstructed points. And we're going to compute the reconstruction error again, so the average between those distances. And then we're going to compare this reconstruction error with the reconstruction error we got from the reference data. And in a moment, I'll show how it actually looks in a notebook. But the idea is that if this reconstruction error goes up, it means that the model has captured the structure of the data that is no longer suitable for compression and decompression. So the structure of the data has significantly changed in a way that the compression and decompression mechanism no longer works correctly. And again, kind of on the other hand, if the reconstruction error actually significantly goes down, then it means that the structure of the data again has changed in a way that the decompression mechanism is better suited than it was on our reference data. So that again means that we have significant data drift or covariate drift. Now let's go to the tutorial. So just to walk you through again, if you go to NannyML and if you go to examples here in repository, and then if you click on webinars, you will see the webinar we have right now today, how to detect drift and resolve issues in your ML models. And then just click on drift detection notebook. And I already have it open here and you can easily follow. You can also run it yourself. So let's get started. I'll give you like a minute or two for people who actually want to follow live. Let's keep this 2 minutes short. Let's get going. So first, I'm going to walk you through kind of the entire process, starting from training the model, just to train a simple model that actually runs on data and actually predicts something. Then we're going to simulate the deployment when we will have a production data set that we have no access to, not during training, not during evaluation, not during testing. And it just comes after and we see what happens with it. We'll be able to see that there is some issues to performance with it. And then we'll go into the main part of the tutorial, which is how to actually detect data drift. So let's start with importing NannyML and just a few things to load the data and things like pandas. We're going to load the data. It is a data set that's available on OpenML organization. It's a very nice nonprofit organization that has a lot of very cool real-life data sets. So very highly recommended that you give it a go. Then we are loading the data. And what we see here is that we have few features about when certain thing happened. And what we're actually trying to figure out is how many people signed up for bike sharing application or actually shared a bike during given season, day, I think it's day. Oh, no, it's hour, during given hour. And we're going to just quickly pre-process the data here. So first thing, we're going to define what's our target, which is the count. And then we'll have to drop some features. First of all, we have to drop the casual and registered features because they actually have very bad memory leak that they just add up to our count. So it wouldn't really make sense to build a model if these two features actually just give us the answer. And because I'm really lazy, I'm just going to also drop everything that is not a number already, which is weather and season. And I'm additionally going to drop the count because that is just the target. So let's do that. Then we're going to split the data, and we're going to split the data in our training, testing, and our production. Because we're not going to optimize on the hyperparameters, there's no need to really do anything with the validation set. So I'm just going to split the data, and I'm going to use time series split here. So we're going to start with the things that happened earlier, and then we're going to test on things that happen later. And then the last part of the data set is going to be reserved for production. And now we just simply train the model of default parameters. We're training LGBM regressor, the most standard thing you can potentially come up with. And we're training that on trained data. We're going to make predictions, and we're going to predict on training, testing, and production. So kind of simulating that we actually have a separate set that we won't see at all. And then we need to prepare the data for NannyML. This is kind of where the NannyML part starts. So what we're going to do first is we need to define our reference data set. And again, as I already mentioned a few times, perfect data set for that is the test data set. So that is exactly what we're going to do. We're going to take the test predictions, test features, and test ground truth. And we define it as our reference data set. And then to analyze, we could analyze just specific part of the data when something has gone wrong, but why not analyze everything to have a bit fuller view? since the data set is not that big. So here for the analysis, we're going to take our production data, the features and the predictions for the time being, assuming we don't have very easy access to ground truth. But right after when we fit our performance calculator, let's just assume we do have access to that. We could also estimate our performance without access to ground truth, but just to show that there are really issues with performance. It's not that we're just estimating and hallucinating issues. There's actual issues. If we try to compute our performance using MSE or MAE, we will actually see that there is issues with our model. So we're going to add targets to our analysis, and then we're going to just calculate the performance, taking the performance calculator and calculating the performance, obviously on analysis with targets. So let me just run it, and you will see here that during testing, everything was fine. So we felt quite confident that we can deploy the model, even though it kind of climbed up at the end, but probably when we train the model, we just look at the total or average performance in our test data set. We don't try to segment in time or do other things like that. So it probably looked fine. But once we deploy it, we'll see that there's huge spikes both with MSE and MAE. So whatever method we use, we see that there's some issues with it. Now, what might have happened? Let's start with the univariate drift detection. So again, I will make sure just here that our predictions are treated as categorical to make sure that we get the right kind of plot. And then our columns that we want to look at, I'm just going to take all the model features and that the model has looked at, just to see what is going on step by step, feature by feature. And then, as already mentioned here, we're going to take our column names as column names, and we're going to compute our recommended metric or method, which is Jensen-Shannon distance. And what do we do then? We will use our univariate drift calculator to fit on reference. And the only thing that it's actually fitting is that it's taking the reference data, and for some methods, it's going to bin them. So you don't have to store the entire thing when you compare it with your analysis data. So if you want to just fit your calculator, let's say you have a few terabytes or a few hundreds of terabytes of data, you can still fit the model or your calculator, and then you'll be able to store just the histograms of the data, which makes storage possible, easy, and then you can easily compare it with your analysis data, which normally will be much smaller. So we'll fit it, and then we'll calculate the results for the Jensen-Shannon distance on our analysis data, and we'll display the results, turning that into data frame. So one way of viewing results is just to manually go over them as a data frame. You can take the data frame and you can do whatever you want with it that you would be able to do just with a typical pandas data frame. So what you see here is that we have our indices. We're going to just split our data by index for our analysis data and our production data. Oh, sorry, for our reference data and our analysis data. So in other words, test and production. And then we're going to have kind of a funny multi-index thing when for every feature we have a potential list of methods, because we can select more than just one method, as you can see here. And we will see what is the threshold for which we consider that something has gone wrong, and what is the value of an actual metric, and what is potentially lower threshold, as some methods might have a lower threshold as well, and whether we see that as something problematic, so whether there's alert is true. So you could just take it and plug it, for example, in your retraining pipeline to automatically retrain if you see that specific things are drifting too much, and you want to retrain and see whether automatic retraining actually fixes the model. So there is some potential for nice automation here. But the other way of viewing the results is just with plots, and the way we do it is we'll take the results, we'll just say dot plot, and the thing we actually want to view is the drift. So we're gonna say that the kind here is drift. and we just show it just like we would show any normal matplotlib or plotted figure. And again, exactly what we saw before. And there's few weird things going on that hopefully help us build understanding of why performance has decreased. So first of all, year is always drifting. In every single chunk of our data, year is drifting, which actually makes sense because it's always monotonically increasing. So it's never going to be the same as the distribution of our entire test set, which already probably gives us some idea of the mistakes we might have made or have made during during training and preparation of this algorithm or of this model. Then we see the same thing happens for a month, is that it always drifts. But in that case, it might make sense because we're looking at kind of a univariate distribution if this data lasts more than a year. But for every period in our data, every chunk, we probably had only 1 or 2 months. So it's drifting. It's fine that it's drifting. It's just cyclical data. But it's good to see that this is actually happening. Then we have hour, which is equally distributed. There's no changes there. We have whether there's holidays or not. And we see that there are probably, again, months when we see a lot of holidays. And it might actually mean that there is something wrong with our models when there's a lot of holidays. But we're not sure yet. For weekday, we see a very weird thing going on, is that this data for testing was probably in some way ordered, but for production, this data was completely not ordered and it's completely random, and it looks exactly as the data for the entire test set. But again, none of those actually exceeds our drift. So we're sure that the distribution of our weekday has not changed significantly, but it's something to look into when you develop your model. And if you see something like that, then probably you should think about whether this is actually something that you're happy with. And then for working day, no changes. It all looks very good. It all stays below the threshold. For the temperature, we see that there are significant changes, and especially there is a big jump here. So again, we have cyclical data, and we already start to build the intuition that we probably build our models to take into account cycles in an incorrect way. And there's something wrong going on when we have different parts of a year-long cycles. Felt temperature, the same thing. Humidity, kind of similar thing. Wind speed, similar thing. So there is something going on with cycles. We already managed to figure out that we probably did not really think through how we're gonna treat temporal data when we develop that model. So temporal data, then let's continue our investigation. And instead of just doing normal multivariate drift detection, let's do multivariate drift detection on all features to get a general view of what is the drift for the entire data set. But also let's drop 2 things that we already know are drifting and have a reason to drift. And there's probably issues with those. So year and a month. So I'm going to run that as well. And then we're going to initialize our data reconstruction drift calculator. So our multivariate drift detection calculator. Just putting all column names for the time being. So not those, but the ones we defined earlier. Then we're going to fit it on reference. So we're going to train our PCA model on reference that's going to learn how the data looks like. And then we are going to calculate. So we're going to run it through the trained PCA on our analysis data. And what we see, there is huge increase in the error. So definitely there is drift, and this drift probably actually is one of the causes for drop in performance. But now let's drop our year and month. So let's do the same thing. Let's fit it again without a year and a month. And what happens? You see that there is actually no drift. So that, what does it tell us? Is that all important drift and all important changes in the model, all covariate shit in the model is really captured in the month and the year columns. And we shouldn't have trained our model, and especially we should not have trained a gradient boosting model on a year, because maybe there is a trend in our application, maybe more and more people start sharing bikes using our application, which is something that you would hope for as a business. But we do not take that into account. And our gradient boosting model just assumed that the higher the year, the more people on average are going to actually share the bikes, but it just took the cutoff on the last data it shows, and it failed to extrapolate this trend further because it's not something that tree-based models can easily do. And the drop in performance is due to us taking our year and month into a consideration here. So this is something that we'll have to think about now as data scientists and try to kind of redevelop the model in a way that doesn't take year and month into account in such a simplistic way. And that's it. We know what happened. We know why it went wrong. And then we can start working on resolution, which in that case would be full model redevelopment, because retraining won't help here. We know that the model would fail later on when we see the next year. And that is it. That is the end of the tutorial. So now, thanks for the listening. We are slowly nearing the end of the webinar. We are still kind of, starting open source library. So I would very much appreciate if you give NannyML a try and give us a star. Every star matters. They give a bit more visibility to our library, which helps more people learn about NannyML, which we see as a good thing because monitoring is important. So that's that. And now, before we go to Q&A, just one more thing. We have yet another webinar on the next Thursday, and this time it's going to be my co-founder, William, talking about what data do you actually need to monitor your models in production. So it's going to be even more hands-on, and hopefully it's going to help you not only understand what's going on with monitoring, but easily get started with it in your job. And now let's get to Q&A. I'm going to leave it up here, and you can just scan this QR code to be forwarded to a form, and we'll send you the recording of this webinar later on.
Thank you so much, Wojtek, for this awesome presentation. It was very informational. We have a few questions here, and just a reminder that you can drop your questions in the Q&A and we will answer all of them live. So the first question for you, Wojtek, is what does it mean that the GS distance is robust to outliers? Is it that it does not detect outliers as drifts? I think
exactly that. That is exactly what it means. If you have a few outliers in your data, and this is something that is not important to you from business perspective or from data science perspective, Jensen-Shannon is going to be robust to those and will not actually flag those as drift. On the other hand, if it's something that you know is going to be important for your data, and even a few outliers can very strongly impact the either business outcomes or your model metrics, you should use something else, such as Wasserstein distance, or it's also called earth mover distance, which is very sensitive to outliers. And that is one of the reasons we have multiple methods in our library, because there's no method that really fits all the use cases. And we also have in our docs quick summary of the strengths and weaknesses of our methods. So then you can take a look there and pick the one that fits your use case best.
Awesome, thanks a lot. I will, after the Q&A, I will also share the link to the doc so that you can have access to this documentation that Wojtek just mentioned. The second question is, in multivariate drift detection, why not using deep autoencoder reconstruction error instead of PCA reconstruction to detect also nonlinear relationship changes as well?
So this is something that is on our roadmap, and it's something that we'll do sooner or later. And the reason we didn't go with it for the time being are twofold. First, PCA is surprisingly robust, works out of the box, and it always has very stable behavior, which is not true for variation autoencoders. If we go with normal autoencoders, there's no chance we're going to get anything that it's in a way meaningful, because even very small change in data distribution will result in huge reconstruction error. For variation autoencoders, they are significantly more stable, so it is possible to do it, but we need our algorithms to work on any kind of tabular data, no matter what is the size of the data, no matter how it's distributed. And to do that, we need to have quite advanced AutoML hidden inside NannyML. And it's much easier to make PCA work with any kind of data distribution and any kind of tabular data than variation autoencoders. So we will have them because, like you said, they are much better at detecting non-linear relationship changes. We don't have now because we need to start somewhere, and we started at the something that's robust and we know it's going to work reasonably well for everything. And in the future, we will have variation autoencoders most likely as part of our library. And of course, if you're interested in that, you are most welcome to contribute, and feel free to join our Slack, feel free to contribute on GitHub. And if you want to go ahead and try to implement those, that would be great.
Awesome. Cool answer. Thanks a lot. Another question was, well, not really a question, but a comment saying very well explained how to use the PCA. So thanks a lot, Eileen.
Thank you.
I hope I'm pronouncing, yes, I'm hoping I'm pronouncing your name correctly, but thanks a lot for that comment. We really appreciate the feedback. We have another question that is a repetition. So what does it mean for the GS distance to be robust to outliers? And then another question is, can you use the univariate drift tests for time series?
Yes, if you detrend and decycle them first. So this is something, again, that is potentially on our roadmap, which is explicit support for time series. If your time series is already stationary, there's no trends, and the cycles are removed, then you can use that kind of data that's prepared in that way that you don't have cycles, don't have trends, and you can put it then directly in Univariable Drift Detection, and you will get reasonable results. As you saw here in the tutorial, if we don't do that and we leave the trend in or we leave the cycle in, we'll get bullshit results. So you have to first do a bit of data pre-processing to do it, but it's absolutely possible.
Nice. Everything is possible, huh? JK. Okay, we have one final question for you, Wojtek. How can you use multivariate drift detection to get interpretable results?
Yeah, so what I recommend is first just run on everything. Then you might want to run it on, you might want to run univariate drift detection, see which features tend to behave weirdly. And then you can do the thing that I did in the tutorial, which is just exclude those and only run it on things that don't change from the univariate perspective. And if your multivariate data detection also doesn't detect anything there, then you can be quite sure that the reason for your drop in performance is not there, because there's no changes in the relationship between features, and there is no change in the actual distribution of the features. So then you are just left with the weirdly behaving features that you see on the univariate level. And what you should do then is use domain knowledge to try to bundle the ones where you know that correlations also matter. Maybe the correlation between the age and income is something that is actually very strongly influencing the model, but the correlation between age and location doesn't matter that much. In that case, select only a few features, 2, 3, 4 features that you know that the correlation between them actually matter for the model. And you can do that using things like SHAP, explainable AI, when you can look at combinations of feature and their importance. And then look at the subset of features that are either important or the interactions between them are important, and run multivariate there. And basically, you should be able to narrow down whether univariate drift actually happens and just it's the change in distribution that influences performance, or whether you find a pair of features, let's say, that don't drift by themselves, but if you put them in multivariate detection, you will see drift. Then you know that there's actual change in correlation between those features, and that's how you get interpretable results that you would miss with univariate drift detection.
Awesome. Very complete answer. Thanks a lot. Great. Then I don't think we have any more questions to address today. So Wojtek, thanks a lot for your presentation. I really appreciate it. Thanks a lot, everyone that joined us today. As Wojtek said, we are an open source library, so don't forget to start us on GitHub if you find this webinar useful. It really means a lot to have one more star there. And if you, just a reminder that if you do want this recording, please scan this QR code, leave us your email, and we will send it by the end of this week. And if you'd like to join another webinar, you will have a chance